Hello everyone. Today I am giving my presentation on a new dead time determination method for gamma ray detectors using attenuation law and generalized dead time models. Here is the overview of the presentation. First, I will define dead time and what are the factors affecting it. Then I will briefly describe two dead time determination methods. After that, I will describe what is dead time measurement with radiation absorption law and the validation of DMRAL method. And then I will discuss the mathematics behind this new method and I will present the results. So, what is a dead time? Uh, a minimum separation time is required for two radiation events to be recorded in radiation detectors. This separation time is called the dead time of the detection system. The detector's dead time depend on two factors. One is the pulse processing time, which is associated with the electronic circuitry of the detection system, and the other is intrinsic dead time, which depends on different parameters like geometry, material, design of the detector, as well as on operating conditions like voltage, temperature. And this dead time effect results in lower observed counts than the true counts. So a mathematical correction is required to make up for the lost counts. That would bring the count rate close to the true counts. So we need correction models. So so far we have two dead time correction models. One is parallelized and the other one is non-parallelized. The parallelizable correction model assumes that if a radiation interaction occurs within the dead time duration of the detection system, then the radiation interaction is not considered or it is not recorded as an individual event and it will reset dead time, hence extending it. In the non parallelizing model, the dead time for a detector system is fixed and interactions that occur during this time cannot be recorded. Now these are the dead time determination methods. One is the two source method, and the other one is decaying source method. One of the most common methods for determining the dead time of a detection system is the two source method. It is used to estimate the dead time of a gas filled detector systems. It can be implemented by obtaining the radiation rate from two sources, both individually and in combination. And the other common method is the decaying source method. It can be applied according to the known exponential decay behavior of a radioactive source using isotopes with short half lives. These are the equations which are used in, in determining the dead time using this method. And in this equation, m e raised to the power lambda p is equal to minus n naught tau m plus n naught. In this equation, the dead time can be obtained from the ratio of the slope to the intercept value. Now we are going to discuss about the dead time measurement with radiation absorption law. This equation I1 is equal to I naught into e raised to the power minus mu of x. This represents, this expresses when a beam of photon penetrates through a material and the transmitted beam intensity is expressed through this equation, where I naught is the incident beam intensity, mu is the linear attenuation coefficient, and I1 is the transmitted beam intensity. In this study, a new method to determine dead time for gamma ray measurement systems is introduced using gamma ray attenuation law and generalized dead time correction models. So, assuming the gamma attenuation law given by intensity um, in the previous equation is expressed by true gamma ray counts, here n1 is the transmitted number of true gamma rays and n naught is the incident number of true gamma rays. This equation 1 can also be written in terms of mass attenuation coefficient mu by rho. Here the mathematical non-parallelizing dead time model with no absorber between detector and the radioactive source can be expressed by this equation number 3. M naught is equal to n naught upon 1 plus N naught tau. If a thin material is placed between the detector and the radioactive source, the non-paralyzing model can be written as equation 4, like m1 is equal to n1 upon 1 plus n1 tau, where m1 is the measured transmitted gamma rays, n1 is the true transmitted gamma rays, and tau is the dead time of the detection system. When we take the ratio of m0 and m1, we obtain equation 5. And when we combine equation 2 and equation 5, we get equation 6, which is written here. Then, if the mass attenuation coefficient of the material and the density of the material are known, then the value of n naught tau can be easily calculated, since m naught and m1 are determined by the detector. So the only unknown parameter is the incident number of true gamma rays n naught after n naught tau parameter is determined. All these calculations are for the non-paralyzing dead time model. And after determining the incident number of true gamma rays, the dead time of the detection system can be determined using this equation 3. Here the experiment design for the radiation measurement system to validate DMRAL method is shown. Here cesium-137 radioactive gamma source is used, whose activity was 370 kilobecquerel. Polyethylene and lead absorber materials were used in the experiment. By individually placing them between the detector and the radioactive source, the gamma ray attenuation measurements were taken using polyethylene and lead as an absorber to determine the dead time of the sodium iodide thallium detection system. The gamma ray measurements were taken for 5 minutes with cesium-137 radioactive gamma ray source at 662 keV for each individual case for the scintillator detection system. 3 consecutive measurements were implemented to reduce statistical errors with and without absorber material. First, the background radiation of the environment was obtained for 5 minutes. Second, the measurements were taken for sodium iodide thallium detector with no material between the detector and the radioactive source for 5 minutes. And these measurements are M0. Then the measurements M1 were taken with the material placed between the detector and the radioactive source before calculating the dead time of detection system for both generalized models. Using the equations we derived earlier, the dead time of this detection system were calculated with the DMRAL method. Here, this table shows the average values of the measured count rates and the net count rates. The average net count rate at 662 keV peak with no absorber was measured as 650.22 count per second with an error of 2.09. This value was used as M0 at all times to determine the dead time of the detection system for both non-paralyzing and paralyzing models. This figure shows the peak difference with and without absorber material between the radioactive source and the detector. This table shows the physical properties of the absorber materials and the calculated dead time values of the sodium iodide thallium detection system for both non-paralyzing and paralyzing models. The dead time value for the non-paralyzing model using the lead absorber was calculated as 8.39 microsecond, while the dead time value for the paralyzing model using the lead absorber was calculated as 8.35 microsecond. So here we conclude that this study introduced a new dead time determination method for radiation detection systems using gamma attenuation law. And in this proposed DMRAL method, it has been observed that the dead time results are reasonable for sodium iodide thallium detection system. In the calculations, non-paralyzed dead time was 8.39 microsecond and paralyzed dead time was 8.35 microsecond using 0.0828 centimeter thick lead absorber. The sodium iodide thallium detection system's dead time values were expected in the range of zero point 0.5 microsecond and 10 microsecond, which shows that our results are like what we expected. These are the references that are being used for this presentation. Thank you.